Hello. In this last section, we're going to speak about the math or the theory behind linear regression. Now, up until this point in time, we've just had a bunch of data and we were throwing a line through it. But what exactly was happening? Where did that line come from? And I just want to give you a quick overview of this. Now, if you don't have a mathematics background, this might look like a real scary looking formula for you, but it's not really all that difficult to understand. First thing you need to know is that we have some records. Now, in the case before with the STEAM data, we had 25 records. So P was 25. We had 25 records. Now, the next thing that we had here was we had a Y value, and the Y value was the amount of steam that was used by the steam plants in a month. And then we also had some input variables that was going to be used to predict the amount of steam that was used. So here's X1. That in this case we started off and it was the number of the average monthly temperature. Now with this we tried to come up with a line that went through the data. Remember, so we had the amount of data, the average temperature in the month, and we were trying to predict what the average steam was. So we came up with let's go back. And we tried to come up with a mathematical formula where Y here was the amount of steam we used. We had that constant term, and then we had also this slope. Remember, that was like minus 0.07 times the average temperature. We also had an error term, remember, because our prediction here was not perfect, so we had an error term. And if I happen to know the amount of the average temperature, and I had this coefficient and this constant term, and I knew what the error was, then I would be able to get the actual amount of steam used to the exact amount. So in other words, I would know exactly how much steam was being used. Now what we're trying to do here is we want to figure out these beta values, or these constant terms. Well, let's go back again. I can't find my mouse. There it is. We're trying to find out these constant terms in such a way that we're going to make this E value as little as possible. So we want our error to be as small as possible. And in fact, what we're trying to do is we're calculating these beta terms up here so that if I square up all of these errors, so I'm multiplying by themselves, this is going to be as small as possible. So we're trying to minimize this error. Now, let's go back real quick. We don't know what the error is. You can't know how much of a mistake you're going to make ahead of time, otherwise you wouldn't make it. So if I did know exactly what my mistake was going to be, I would know the exact value of Y. But unfortunately, we don't know what that error is, so we can't put that into the formula. So instead, what we're going to do is this Y hat value is nothing more than an approximation. It's not going to be Y, it's going to be close to Y because we don't know what the mistake is. So we're going to call that guy Y hat. Y hat is an approximation. So let's go back real quick to our let's just do this. Let's just go old school here. Let's go back to our Microsoft Excel, and remember we had all of this data here, and this was the average temperature, and then we were trying to predict the steam usage. And remember, when we calculated that, Excel told us that if you multiplied the steam or the average temperature by this number right here, and added the number of 13.6 to it, that would be a real good approximation for the steam use. So let's kind of go back over here to the next thing, the next tab, and here I'm going to do is I'm going to take and multiply this guy right here by 0.0798, negative 0.0798, and I'm going to add 13 to it, and I get this answer. So if I use the formula, I get this answer. Now let's just move over here. I'm copied this guy over here, and I've copied this guy over here. So this is what I wanted to get, and if my formula was this, and by the way, here's what my error was. And if I happen to know ahead of time what my error was, I could have just added this and gotten the right answer. But we'll never know what the error is ahead of time. So the best we can do is predict, have an approximation of what the true value is. Now, recall that what we're doing here is we're trying to make it so that our error is as little as possible, because we won't know what it is, so let's make it small. And what we're doing is we're trying to make it so that our error squared value is as small as possible. So when you run a regression, you're going to get a predicted value with a very small error squared value. And if we remember right over here, I said, hey, you know what? In the real world, you're allowed to alter these predictions for business reasons or whatever. So do you remember in one of the previous videos, I took these numbers right here and I said, well, there might be a business reason or a government regulation that says I can't use 0.07, and then I have to use negative 0.1. So I changed this thing a little bit, and then maybe I also took this guy right here instead of 13.6. We had a business rule that it had to be 13. So what happened was now my prediction is a little bit different, and my error square value now increased to 92. Remember that when left to the mathematical formula, the regression, it was a very small number. When I start to mess around with it, it's going to go up a bit. So in this case, it went from 18 to 92. That's what's going on with regression here, is I'm going to try to minimize those errors. Now, just because this is the smallest possible error with our training data set right here doesn't necessarily mean that this is the best model. It just means this is the best fit for the training data set. Again, there might be some business reasons or common sense or domain knowledge that might make you want to change these numbers like we did right here. And just because it doesn't fit this data perfectly doesn't mean that it's a worse model. It just means that there might be other considerations. So let's go back over here, and you can see that, again, we are going to try to predict what the y hat, we're trying to get as close to y as possible, and we're going to be predicting y hat as an approximation of y. So let's take a real quick look at, remember we then added a second data set, or a second column. So originally we were trying to predict the amount of steam use with the number of days, or the average temperature in the month. But then we added another variable here called the operating days. So this is how many days the plant was open. So what we have here is now we're going to have two variables to try to predict the steam usage. Now I want to give you a couple of terms to know. The first term I want to say is independent variable. You're going to hear this sometimes in the real world. What's an independent variable? An independent variable, I call those input variables because they go into the model. So think independent input into the model. That's what those things are. A lot of people, if you're a pure statistician, they will drop the term independent variable all the time, but a lot of times in the real world, they just call it an input variable. So it's important to know the nomenclature or the terms that are used, just in case you start running into a pure statistician. You'll know what that, you don't have to give them a blank stare when they say independent variable. The other thing what we want to say is dependent variable right here. What's a dependent variable? That's the thing we're trying to predict. I keep calling it a target variable. This is dependent because it depends on, our approximation of this guy depends on this and this. Now, if you come from a predictive modeling background, you would call this guy an input variable, and an input variable, and this is a target. If you come from statistics, this is independent, this is independent, and this is dependent. Now, another term to watch is multivariate regression. You're going to hear that term an awful lot, especially if you start hanging around with statistics people. What's a multivariate? It's simply a case where, I don't know where, oh, there it is. I'm sorry if I keep shaking my mouse. It keeps disappearing on my screen. I know it's not disappearing on the recording. But anyways, so the multivariate regression, what that is meaning is that it's you have more than one input variable. You have more than one independent variable, and as soon as you got two of them, it's now called multivariate. There's nothing special about it. There it is. So there's nothing special about multivariate regression. It just simply means I got, as opposed to originally, I had an X value, the amount of days, the average temperature in the month, and now I have a second variable, which is the amount of days that the plant was open. As soon as I go from one variable to two, it turns into multivariate regression. Now, there's no real easy formulas for solving the multivariate regressions. You could find simple one variable regression, the formulas for that all over the internet. It's real simple stuff. But then when you start getting into more than one variable, you have to start using what's called linear regression, not linear regression, matrix algebra to solve this. And it's not real hard, but as you start getting more and more variables, it becomes necessary to use a computer. And you'll never need to do that by hand. Computers do a lot of that for you. But it's, so it's beyond the scope of this class to talk matrix algebra. Now, remember, let's go back over here to this guy right here. This is our formula. Remember, we have this y hat variable, and beta 0 is plus beta 1 times x1, beta 2 times x2. Now, when we ran our ANOVA, remember when we did this with our Excel, Excel came up with 9.12 plus x times negative 0.07 plus w times 0.202. That is the formula. If I plug these values in, then I get this guy right here. I can get this formula. So this is the formula that we're going to use to predict y. We can't get y because we don't know what the error is, but we can get pretty darn close, and pretty darn close we call that y hat. So let's look at some of the other, when you get this kind of output, when you run a regression, you will get a table like this. This is called an ANOVA table. I'm going to give you, there's lots of numbers in here. Not all of them are important or useful to you, so we're going to go through and what they all mean so that you can understand this going forward. So we've already talked about the coefficients right here. This is so we can come up with the formula. Well, what else did we look at? Well, we've already looked at this as well, as the significance. Is the model any good? Well, the model, we just look up here, 0.9 or 9.22 times 10 to the minus 10. That's a really small number. This tells us how good is the overall model. Now, the best way to think about this is just think about that number as what's the probability that this model is actually bad? That's probably the best way to think about this. And this number is really small, so that means it's a really small chance that this model is really a bad model. What's a good model? What's a bad model? Usually, not always, but usually people use the number 0.05. And if you use this number, if this number right here is less than 0.05, you can usually assume it's a good model. And typically, if it's bigger than that, you say it's not a good model. In the real world, however, if it's larger than 0.05 and you're making money, people don't lose a lot of sleep over that. But when you start looking into some other areas like drug studies or medical research, then that number becomes a lot more important. They really want to, it depends on what industry you're in, really factors into what's a good model and what's a bad model. If you're selling Twinkies and you're making a lot of money with a model with a significance value of 20%, 0.20, that's really not a good model, but hey, you're making money, and you know what? You're selling Twinkies. How much harm could you be doing? So it just really depends on the industry, and if you were doing something like selling some kind of a cancer drug, probably you want to keep that number as low as possible. Also, let's take a quick look over here to the variables. You can look, I have three variables. This is the constant term. This right here is the number of days, or the average temperature, and this is the number of days the plant's open. All three of these numbers are very small. This one's 10 to the minus 8th, 10 to the minus 9th, and this is 0.00021. All three of these numbers are a lot smaller than 0.05. So we can assume that these variables actually are pretty good at predicting the amount of steam that was used in the plant. If the number is larger than 0.05, a pure statistician would say, well, this isn't a statistically predictive variable. It's not statistically significant. You know what? Again, if you go to the real world, they don't really care so much about that statistical significance. When Fisher was the gentleman or the scientist who originally came up with this concept of a statistically significant variable. And when he came up with that idea, what he was really saying is, look, if it's not statistically significant, take a second look at this thing and decide if it should be in the model or not. It's not, again, a religion. You don't have to do that. But, it's like a red flag to decide if a variable should be taken out of the model or not. If in other words, if this guy here is not statistically significant, then you don't have to take him out. It's just you're supposed to take a second look at it. Reality is, a lot of times statisticians consider this to be a sacred number, and you take the thing out if it isn't statistically significant. Real world, not the case. The real world is you use common sense, and this is nothing more than a red flag to take a second look. A lot of statisticians will look at this as, if it's a sacred number. Let's also talk about confidence intervals. What are those? Confidence intervals, I'm going to explain these just because people don't know what they are. But a lot of times in your output from a regression, you will get a confidence interval. So what does that mean? Well, for example, my intercept here was predicted to be 9.12 whatever. Now, in reality, the real number, this is nothing more than approximation from the data. The real number is going to be something different. We'll never know what the true number is. However, from the data and the distributions, it can be calculated what the range of it is. So we'll come over here, and even though this is the number that we calculated, this is probably not the exact number, but we are 95% certain that the real number is more than 6.8 and less than 11.4. So we know that the real number is probably in this somewhere. Same thing with the next value, x. We calculated x to be this. That's probably not the real number. We're going to use it because it's a pretty good number and it gives us the lowest error squared. However, that's probably not the real number. The real number is probably closer to, and where did my mouse go again? We'll wait a second for it to come back. There it is. Okay, the real number is probably greater than negative 0.08 and less than 0.05. And then we go one more to w here, and that we calculate that 0.202. That's probably not the real answer, but the real answer probably is somewhere between 107 and 0.297. And again, in the real world of predictive analytics, confidence intervals aren't really used that often, but I just wanted to explain those to you. Finally, let's take a look at R-squared and adjusted R-squared. We talked about these before, but let's talk about them one last time. What is this R-squared value? R-squared value in this case was 84.9. What does that mean? It means that our model is able to explain 84.9% of the changes in Y. So that's kind of a hard way to think about it. The variation on Y can be explained. Our model explains 84.9% of the variation in Y. That doesn't have any intuitive appeal to it. So a better way to think about this, it's not precise, but this is a way a lot of people think about it. Think about it that your model is 84.9% accurate. Again, that's not precise, but that's how a manager might think about that, and there's nothing wrong with thinking about it in that capacity. It's just a way of saying, look, it's a way to understand how good your model is at predicting what you're trying to predict. Now, remember in our previous video we had R-squared, and when we added another column of random variables, this R-squared value got to be better. Why is that? Is the more variables you throw at it, even if they're random, it will make the R-squared value go up, or if it will never go down, it will either stay the same or it will go up. Your R-squared, the more variables you throw at it, the better your R-squared. So that means that you can't really compare two different models that are that have different number of parameters. If you have a guy with 2 variables and a guy with 3, remember we already had that case where we had 2 and then we added an extra column of random numbers. Well, you would prefer to have the guy with 2. You want the guy who doesn't have the random number. If you just look at the R-squared value, you'd be choosing the 3 column instead of the 2. So what we have is an adjusted R-squared, and what that does is it penalizes you for having more and more variables in the model. So it looks at the R-squared and it starts to penalize you a little bit for every time you throw a new variable in there. So if you're going to compare two models to see which one is the best, you would use adjusted R-squared. This is how you compare different models. One of the ways. We'll talk about other ways shortly. And the other thing is we have R-squared, which is just sort of a good idea for you to understand how predictive your model is. So we're going to stop here, and then we're going to talk in our next discussion on the assumptions of linear regression.